In this video, I'll be talking about the Leibniz's integral rule, and the purpose of this integral rule is when you want to take the derivative of an integral. So for example, you want to take the derivative with respect to x of some integral, which is here, and the limits are generally a function of x. So they might be constants, but in general they might be depending on x. So if you're integrating from a of x to b of x of some function hxy with respect to y, and you want to take the derivative of this integral, one way to do it is you first compute this integral and then take the derivative. But if you want to reduce effort and try to take the derivative first, then the rule says take the derivative of the upper limit, which is sitting right here, and then substitute the upper limit inside the function, which is here, and then minus, take the derivative of the lower limit of this lower limit and substitute the lower limit in the function inside, and then the third term is just the same integral, but we have moved this derivative inside. So notice that if a of x and b of x were constants, their derivatives here and here will be 0. So you could directly move the derivative inside the integration. So let me give you an example. For instance, if you want to do d over dx of an integration from 0 to infinity of e to the negative x plus y dy, we could simply move this derivative inside the integral because the limits are constant. So we could just simply say this will be 0 to infinity d over dx e to the negative x plus y dy. So you can see this from the rule. So if you follow this rule, the derivative of the upper limit will be 0, which makes the whole term 0, minus the derivative of the lower limit will be 0, which makes this term 0, and the third term is just the same integral with the differentiation moved inside the integral. So if things were constants in the limits, you could easily move the derivative inside. But if the limits are not constant, then you need to follow this rule. So let's do some other examples which can help you show how useful this rule can be. So let's say, for example, you want to do d over dz of some integral from 0 to infinity x minus z to infinity of some function e to the negative x plus y dy and then dx. So again, you have the option to first integrate this, compute the double integral, and then take the derivative with respect to z. But that might take a lot of effort by computing this integrals and then taking the derivative. So it might be simpler in many cases where you could move this derivative inside, do the differentiation first, and then compute a simpler integral. So if you follow this rule that we have just written, so notice that the limits here are constant. So we can move this differential one step inside without any problem. So we can just simply say 0 to infinity d over dz and the inner integral stays as it is, which was x minus z infinity e to the negative x plus y dy and then dx as it is. So you see we have moved the derivative one step inside without doing anything because the limits were constant. But the next step requires, but now when we want to move this derivative inside, we cannot directly do this because the limits depend on z. So we need to make use of this Liebniz integral rule. So let's make use of the rule. The outer integral stays as it is. Now, first thing is we take the derivative of the upper limit, which is 0, and that makes the whole term 0, minus the derivative of the lower limit, which in this case is minus 1, because we are taking derivative with respect to z, times, you have to substitute this limit in this function. But this function inside here is a function of y, and that's because we are doing dy. So instead of y, just substitute x minus z. So the function will be e to the minus x plus x minus z. Now the third term is you take the derivative inside. So the integral is as it is, x minus z to infinity d over dz of e to the negative x plus y dy, and then dx for the outer integral. And notice that the derivative with respect to z of this function of x and y is 0 because there's no variable z here. So this integral just breaks down to the integral of 0 to infinity e to the negative 2x minus z dx, which is much simpler to compute as compared to the original problem, which is the derivative of this double integral. So this is where Leibniz's rule might be useful in many practical problems. So I'll do another example just to illustrate when we might have to do this multiple times. So for example, you are required to do d by dz of the integral from 0 to z over 2, and then the inner integral is x to z minus x e to the negative y dy dx dx. So notice now the limits depend on z, so we cannot directly move this derivative inside. So we need to apply the Leibniz rule. That means we take the derivative of the upper limit, which in this case, differentiating z over 2 with respect to z will give you 1/2. And then we need to substitute z over 2 in this function here. And this function is just a function of x because you're doing dx. So let's substitute x equals to z over 2 here, which makes this x equals to z over 2 to z minus z over 2 e negative y dy. The second term will be minus, the lower limit is 0, so that's great, plus, now we can safely move the derivative inside. So it will be 0 to z over 2 d over dz of this inner integral. Let me do it with another color here. So it will be again x to z minus x e to the negative y dy, and then the outer integral at dx. So we've effectively moved this derivative one level inside. So notice this integral is from z over 2 to z minus z over 2, which is again z over 2. So this term will give you 0. So we are left with just the third term, that is 0 to z over 2 d by dz x to z minus x e to the negative y dy dx. So this will be, so let's put the outer integral in blue, 0 to z over 2. Let's put dx somewhere here. So again, for this inner derivative of the integral, we need to use the Liebniz rule. So taking derivative of the upper limit with respect to z will just give you 1. And then substituting the upper limit inside was a function of y, so we'll get e to the negative z minus x minus the derivative of the lower limit. The derivative of x with respect to z is 0, plus, now we can safely move the integral inside, derivative inside. So x to z minus x times d over dz e to the negative y d dy, and notice again derivative of e to the negative y with respect to z is 0. So this integral just reduces to 0 to z over 2 e to the negative z minus x dx. So notice that this thing here has just reduced to computing this much simpler integral, and that is where the power of Leibniz's integral rule lies.